All right, so moving on to modeling with functions and graphing functions. So if you remember from yesterday, a function is a relation where each input has exactly one output. And we discussed various ways of identifying whether a relation is a function or not, given ordered pairs or given a graph. We're going to dive right back into functions. We're going to dive right back into some vocabulary. So get your notebooks ready and make sure you're taking good notes. All right, let's first talk about independent variables and dependent variables. These are the two types of variables that we'll encounter when we're dealing with functions. And I always find that it's easier for me to explain what an independent variable is and what a dependent variable is by using an example. Okay, you could read the definition yourself and write it all down, but let me go ahead and use an example on what an independent variable is and what a dependent variable is. So the main thing that you need to remember about independent variables and dependent variables, well, you also need to remember the top sentence. Input is going to be your independent, output is going to be your dependent, but really the value of the dependent variable depends on, or is a function of, and we're going to talk more about this in a moment, the value of the independent variable. So let's say I had an hourly job. If I had an hourly job and I made some money, so we would have two variables. Okay, the two variables would be M, the money I made, or the money I make, and H, the hours I work. Okay, now what variable depends on the other? Does the amount of money I make depend on the hours I work? Or does the hours I work depend on the amount of money I make? That second statement that I just said, that doesn't really make any sense, right? The hours I work depends on how much money I make. Okay, if we're talking about this in the context of a career, of a job, right, I would not have any money until I've worked hours. So in this case, it's easy to see that really the amount of money I make is going to be completely dependent on the amount of hours I make, the amount of hours I work. The more hours I work, then the more money I make. The less hours I work, the less money I make. So your dependent variable would be the amount of money you make, because the amount of money you make depends on the amount of hours you've worked. Whereas your independent variable would be the amount of hours you work. That is not dependent on anything. That's just the amount of hours you work. Your money that you make is going to be dependent on the amount of hours you work. Let's do a few more. So identify the dependent and independent variables in each situation. So in the winter, more electricity is used when the outside temperature goes down and less is used when the temperature rises. So what are our two variables? Well, it looks like the amount of electricity is one of our variables, and the other variable would be the temperature. Okay, so is the temperature dependent on the amount of electricity, or is the amount of electricity dependent on the temperature? Well, let's think about this. The temp, if you were to write this down, the temperature is dependent on electricity. Would that make sense? Okay, what you're saying there is the more electricity you use, the higher the temperature is, as if you could somehow control the temperature yourself. Okay, that would obviously make no sense. Okay, in this case, your independent variable is going to be the temperature, whereas your dependent variable is going to be the electricity. The electricity depends on the outside temperature. Okay, so your dependent variable is going to be electricity, and your independent variable is going to be your temperature. Next, the cost of shipping a package. The cost of shipping a package is based on its weight. Okay, so here the cost would be dependent on the weight and not the other way around. Okay, the weight would be independent. So weight would be your independent variable, whereas the cost would be your dependent variable. And last, the faster Tom walks, the quicker he gets home. So here we have the faster, that would be speed. The quicker he gets home, that would be time. Okay, so what depends on what? Does speed depend on time, or does time depend on speed? Well, in this case, the time is going to depend on the speed. If he walks faster, he's going to get there sooner. If he walks slower, he's going to get there. It'll take him longer to get there. So your dependent variable is going to be time, and your independent variable is going to be speed. So hopefully that clears independent and dependent variables at least a little bit up. Let's move on. function notation. So function notation is just another way of writing an equation. All right, here we have an equation y equals 2x minus 8. So to write this in function notation, you would use this notation right here, which we would read as f of x equals 2x minus 8. So here we're just writing the function of x equals 2x minus 8. And hopefully this makes a little sense because remember, y is your dependent variable. It's dependent on x, and that's why we could read this as the function of x. Okay, your y is always going to be dependent on your x value. Your output is going to be dependent on your input. And that's why we could use function notation. But really, these two are interchangeable. They mean the same thing. And you would read this as f of x, or the function of x. So if I was reading this right here, I would say f of x equals 2x minus 8. And you've heard me say that before, and you've probably seen this before, but it means the same thing. And we're going to work with this during the next few slides as well. So now we're going to be writing some equations using function notation. It's very similar to what we did last week, except instead of y, we're going to be using f of x. So here we have a lawyer's fee is $180 per hour for his services. How much does the lawyer charge for 5 hours? So really we only need that first sentence to write the equation portion of our problem. Per, remember, is one of your rate words. It means multiplication. So we would write this as f of, and I'm going to use the variable h, since we're talking about hours, equals 180 times h. That's 180 per hour. Okay, remember h is your independent variable. This f of h here is your dependent variable. That's why it's a function of the amount of hours that you actually see the lawyer. So to solve this, all you would need to do is plug in 5. But before we do that, let's make sure we identify what our variable stands for. H in this term is hours. So we need to define our variables anytime we're doing these type of problems. All right, now let's go ahead and plug in 5. So what we would do is we would just put 5 anywhere we see an h. So it would be f of 5 equals 180 times 5. And that would give you the total charge for working with this lawyer for 5 hours, which would be $900. And let me just put 900. Let's bottom example. Okay, the admissions fee at a carnival is $9. Each ride costs $1.75. So that's really the only piece of information that we need to write the equation part of this. So what would this look like? It would be f of x. Okay, admission costs $9 fat, so that's going to be 9 plus, and then each ride, each would mean multiplication, each ride costs $1.75. So 1.75, and we had to use x since I used x over here. 1.75x. This is just similar to what we did last week. Define our variable. X equals the number of rides someone goes on. All right, and then solve it. So it says how much does it cost to go on to the carnival and then go on 12 rides. So all you need to do is plug in 12. F of 12 equals 9 plus 1.75 times, I'm running out of space here, times 12. Okay, and if you do that, you would get f of 12 equals $30. It costs $30 to go on 12 rides. All right, let's talk about reasonable domain now. And, this is especially important in terms of real-world type problems, because with real-world type problems, it wouldn't make sense for us to have certain domain values, and we'll talk about that in just a moment. But remember from yesterday that domain is going to be your input or your x values, whereas range, your output, is going to be your y values. Okay, so now let's go ahead and read this. A telephone company charges 25 cents per minute for the first 5 minutes of a call, plus a 45-cent connection fee per call. So that doesn't depend on the minutes. That's just per call. Okay, write a function for the total costs in dollars of making a call. So first we're going to write this in function notation. So I'm going to write f of m equals, well, it's 25 cents per minute. So that means we'd have to multiply 25 cents or 0.25, 25 hundredths times the amount of minutes that we talk on the phone. And then plus just a 45-cent connection fee per call, right? And this is all stuff that we did last week. But now what we want to do is we want to talk about reasonable domain values, reasonable range values, okay? So if we think about this, would it make sense for us to maybe have a negative m for our domain? Would it make sense for me to say m equals -7? Can we talk -7 minutes? No. And this is what we're talking about when we talk about reasonable domain. Would it make sense for us to talk -7 minutes? Okay. So a reasonable domain value for this case, our domain, reasonable domain, would be starting at 1. We wouldn't have any negatives. Wouldn't have 0 either, because if we had 0, we'd still have to pay a connection fee, but we wouldn't even have a call, so it wouldn't make sense for us to talk 0 minutes. So 1 would be a reasonable domain, 2 would be a reasonable domain, 3 would be a reasonable domain, 4 would be a reasonable domain, 5 would be a reasonable domain. Now, why wouldn't 6 be a reasonable domain? Why would I stop at 5? Well, I would stop at 5 because of the context of this problem. It says that this is a charge that they're gonna charge you for the first 5 minutes. After the first 5 minutes, the charge is going to be different. We don't know what it is. They don't tell us that, but it's going to be different. For range, all you would do, and this is what we did today, is just plug in all of these domain values, and I'll just go ahead and plug them in for you because I don't want this video to be too long, but you could do that on your own as well. And if you do that, you'd get these range values. And there you have it. Reasonable domain, reasonable range. That's what makes sense. Okay, now let's go ahead and talk about graphing functions, and we've done a little bit of this today. But today we're going to graph equations, and we're going to put them on a coordinate plane. So to graph equations, all you're going to do is plug in all of these values into your equation and figure out what your y value is going to be. You're going to plug in the input and figure out your output. Okay? So if you plug in -1, you'd have y equals 2 times -1 minus 3, which that would be -2 minus 3, which is -5. Okay? You plug in 0 next, that would be y equals 2 times 0 minus 3, okay, which would be 0 minus 3, which is -3. You plug in 2, it would be y equals 2 times 2 minus 3. 2 times 2 is 4, and 4 minus 3 is 1. And last, you plug in 4, it would be y equals 2 times 4 minus 3. 2 times 4 is 8, and 8 minus 3 is 5. Okay, then graph these ordered pairs on a coordinate plane. So this would be -1 comma -5, 0 comma -3, 2 comma 1, and 4 comma 5. So -1 comma -5 would be right here. 0, -3 would be right here. 2 comma 1 would be right here. 4 comma 5 would be right here. They gave us a specific domain, so we're not going to connect these with any lines or whatnot. This is going to be an example of what? Discrete or continuous? Hopefully you said discrete. This would be an example of a discrete graph. It's just a set of points on a coordinate plane. So I'm going to start this problem, and I want you to finish it at home after I've started it. So here we have -3x minus 5y equals 20. And when you're given an equation like this, it's easier, it's sometimes easiest, especially if we're using a table, to put this in what we call slope-intercept form, which you might have heard about before. Slope-intercept form is y equals mx plus b. And this format is actually going to help us out a lot when we start graphing using slope-intercept form. Why is it easier to do it that way? Because remember, y is your dependent variable. It's dependent on your input. So, sorry I had to cut it off because announcements are starting. But we are solving for y every time, right? So if we already have y by itself, we just need to plug in x, and we don't need to worry about moving or manipulating anything or solving any equations. We're just plugging in x and going along with that. So there is a section in the book titled Literal Equations that we actually skipped, and it shows it really helps us move variables around in an equation, and we're going to get back to that section when we start talking about slope-intercept form and we're trying to change equations to slope-intercept form. But really, all you would need to do, if we have -3x minus 5y equals 20, and you're trying to get y by itself, you perform the same steps that you would if this was just a regular equation. We want to get y by itself. We want to get rid of everything else. So we would want to get rid of the entire negative 3x. We want to change the entire negative 3x to a 0 to get rid of it. So we'd have to add 3x on both sides. And if you do that, you'd be left with negative 5y, because that would cancel out, equals 3x plus 20. Okay? Y is not by itself yet, so we'd have to divide by negative 5 on both sides of this equation. And if you do that, you would get y equals negative 3/5 x minus 4. Okay, and then from there, you do the same thing that we did in our last example, which is plug in negative 5, plug in negative 4, plug in negative 2, and plug in 0 to fill out the range or the output portion of this table, and then graph it. This video is already pretty long, and I don't want to increase your homework any more than I have already. So I'm just going to stop it here, finish the rest of this table yourselves, and I'll check it tomorrow when I check your notes. Have a great day. See you tomorrow.